Okay, guys, I have a couple of questions. I got a couple of questions from you, and I just want to go ahead and go over these. So, for naming alkanes, all what you need to do is choose your longest carbon chain and start from the end that gives the first substituent the lowest number. So, it's going to be this end here, and you go by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 is decane, so decane is going to be at the end. This is the end of the naming. And then now your substituents in there. This is the branches that are coming off your main chain. So you have a CH3, you have an ethyl group, you have a CH3, and you have two ethyl groups. You have to arrange those in alphabetical order. And we're going to group all the CH3s that are the same. So the CH3 is called a methyl, um, and this is called an ethyl. E comes first, so I'm just going to go ahead and arrange in alphabetical order and say that the ethyl is on carbon number 3, dash. And then on carbon number 3, actually on carbon number 3, 5, and 7, I have those four methyl groups. So it's going to be 3, it's going to be 5, and it's going to be two sevens in there, not one 7, because every substituent should have a number. It's going to be a tetramethyl because it's four methyls in there. It's going to be a tetra. Just going to remove that. It's going to be a tetramethyl, and it's going to be a decane. Guys, remember that numbers are they are spaced from each other by a comma, and the letter and the number they are spaced from each other by a simple hyphen. Okay. For naming bicyclic compounds, this is an example of a fused bicyclic system because it does have two carbons in there, so they are connected by two carbons. This is two cycles in it, cycle 1, cycle 2. This is an example of a bridged bicyclic system because this is one cycle and this is another cycle, and this is your bridge in there. Again, these two are bicyclic systems because they are connected by two carbons as well, but the difference is the two carbons here, they have one carbon in between versus a zero carbon in there. So these two, we're going to call them bicyclo. So you start the name with a bicyclo, and then you open the brackets. So it's going to be bicyclo, and you open the brackets in there. Of course, any substituent, you're going to put it before the bicyclo. So I didn't leave a space for myself over here. So I'm just going to go ahead and put a space so that I can put any substituent in there. When you start your numbering, you always start your numbering from either these 2 points of connection, either one of these, either this one or the other one. And let's say, for example, if you start, I don't care about the substituent here. I care to start my numbering either from here or from there. However, you're going to always move to the side with more carbons. And if the side with more carbons is closer to the substituent, then you want to make sure to start your numbering from down there rather than from up here. So I'm going to start carbon number 1 here, and that is going to be 2. So I want to give that substituent the lowest number. It's going to be 3, 4, 5, and 6. See what I did? I finished numbering the first cycle before going into the second cycle. Now for the second cycle over here, it has less carbon. So I always start numbering the more carbon cycle and then the less carbon cycle. I start numbering from the point of connection and start numbering from the point which is closer to the first substituent. Now I want to move over here. I can do 6. Since this carbon over here is closer and it does have a substituent, then I'm going to go 7 and I'm going to go 8. So the total number of carbons here is 8 carbons. So 8 is octane. So I'm just going to put octane at the back, at the end in there. And then bicycle, I open the brackets. In the brackets, I need to include the number of the carbons on each side of these two connected carbons or two carbons in connection. So on this side, I have 1, 2, 3, 4 carbons. You list those numbers from the highest to the lowest. Comma. On this side over here, I have 2 carbons, so this is a 2. And then, this is very important, you need to have 3 numbers in there. between those 2 points of connections, there is no carbon in there. It's a zero. The zero is important because it tells me that this is a fused bicyclic system. And then I put my substituents on carbon number 2 and 7. I have a dimethyl group. So it's going to be 2,7-dimethyl. There's no space. It's a dimethyl and then bicyclo 4,2,0 octane. This is a bridged bicyclic system over here. So if you take a look, I mean, on this side I have 2 carbons, on this side I have 2 carbons, and on this side I have a 1 carbon. I'm going to go with this side first because it doesn't have a substituent. So I'm going to start numbering here so that I give my substituent the lowest number. It's going to be 1, 2, 3, and 4. So I finished my first round before I go to the second round in there. From the more carbon cycle to the less carbon cycle. So I cannot go 5 here because this cycle here has 1 carbon versus here it does have 2 carbons. So I need to finish that. So it's going to be 4. Keep it. So you're moving this way, right? So it's going to be 3, 4. Keep your movement the same. So it's going to be 5 and this is going to be 6. And now that is going to be 7. So I know that this is a bicyclic system, so it's going to be a bicyclo. And then we're going to open the brackets. Before opening the brackets, let's put the substituents on carbons 2 and 7. You do have the dimethyl. So it's going to be 2,7-dimethyl and then bicyclo. Okay, so between those 2 points of connection, I have 2 carbons here, 2 carbons there, and then 1 carbon in here. So it's going to be a 2, 2, and a 1. See, this 1 tells me that this is a bridged bicyclic system versus a 0. That tells me this is a fused bicyclic system. And then it's going to be a heptane. And then you have the last case of the bicyclic system where you have a spiral. So spiral is whenever you have 2 cycles connected with 1 carbon versus 2 carbons in here. The rules in the naming is different because you start numbering from the, not from the point of connection, but you start numbering from the first carbon of the lowest carbon cycle. So this is going to be the lowest carbon cycle. This is going to be the highest carbon cycle in there. So the lowest carbon cycle has 2 carbons versus the more carbon cycle has 4, 5 carbons in there. So you have 5 carbons in here. And then I need to start numbering either from this carbon or from this carbon. But what determines it is if you have a substituent. If you have a substituent, start numbering from your substituent to give your substituent the lowest number. So it's going to be 1, it's going to be 2. Finish numbering your first cycle in there before you go into the second. And when you go into the second, just make sure to give the lowest number to the carbon that has the substituent. So see, I will go 3, 4 like this and not 3, 4 like that. So you go by 3, this is 4, this is 5, this is 6, this is 7, and this is 8. And what I have here is a 1, 4 dimethyl, and it's going to be spiral. And then I'm going to open the brackets in there. Now, see the difference here. You go with bicyclo from the more carbon to the less carbon, and it's always 3 numbers. For the spiral, you go from the less carbons to the more carbons. So on this side, I have 2 carbons, and on this side, I have 4, 5 carbons. So it's going to be 2, 5, and it's only 2 numbers in there. And then the total number of carbons is 8, so it's going to be octane. Okay, now the second question that I got is drawing the Newman projection. How to draw the Newman projection if you have a skeletal form. It's very straightforward in there, so it's up to you to view your skeletal form either from the left or from the right in there. I'm going to view it from this end since I am numbering it from this end based on nomenclature. I need to give the first substituent the lowest number. So it says like a draw or change the Newman projection, and I need to specify the carbons around that Newman projection. It's between carbons 2 and 3. So what I have here is carbon number 2 and then carbon number 3 in there. So you start with let's go ahead and draw a circle in there. Always, whenever you want to change your Newman, you always want to draw the staggered. Don't draw the eclipse, draw the staggered. And then from the staggered, you can simply rotate and get your most stable conformation. Newman, most stable Newman conformation. So on carbon number one, so carbon number one is the first one that I see. So this is gonna, I'm sorry, carbon number two is the first one that I see, which is this one over here. So what is on carbon number two? As I see it, I draw it. I will have a, remember that there is also a hydrogen in there. So this is gonna be a hydrogen. And on three, there is a hydrogen as well. Okay, let's put the hydrogen on the other side. So you do have a hydrogen here, and you're gonna have a hydrogen in there so that you would easily see that. So on carbon number two, what do I have? I do have a two methyl groups in there, and I do have a hydrogen, and then it's connected to three. So let's go ahead and draw it. So carbon number two has two methyls. So I do have a CH3 up there. So it's going to be my CH3. It's going to be my methyl. I have another methyl in here. So this is going to be another methyl there. This is going to be my CH3 over here. And then I do have a hydrogen. Okay. And then on carbon number three, I do have a CH3. I do have an ethyl group, but remember what I told you earlier, that your longest carbon chains, whether you go this way or you go this way, your longest carbon chain is always to be on the vertical line. So that is your carbon number three in there. Carbon number three is at the back. So carbon number three, the way that I'm seeing it, it does have a hydrogen in there. So this is going to be your hydrogen. Okay. I'm just going to go ahead and draw the this group here, which is the ethyl group. I want it to be on the vertical line. It's easier for me to view the longest carbon chain. It's going to be a CH2, CH3, and then my CH3 is going to be over here. Good. Okay. So when I ask you go ahead and draw the most stable Newman projection, what you do is you look at both carbons, carbon 2 and carbon 3. With carbon number 2, you want to make sure that the highest group on carbon number 2 is basically up there. And the highest group on carbon number 3, or highest atomic mass group on carbon number 3, is down there. They need to be 180 degrees away from each other. So if they are 180 degrees away from each other, I cannot call this anti because you do have other groups in here. You do have a CH3, you have another CH3, so you do have gosh here, you do have gosh there. But still, these two groups are 180 degrees away from each other. So I would say that this one's going to be the most stable in Newman projection for this structure in there. Okay, that is the most stable in Newman projection. Most stable means the least energy, and always the least energy is the staggered and not the eclipse. So it's going to be the staggered and not the eclipse. So now if I'm looking at this and I want to determine what are the energy for this structure, guys, there is a table that I posted in there. This is the table over here. You see this on your OWL homework. So what you're looking is basically the energy strain in there. You don't have any eclipse, so what you have is the staggered. Oh, I don't see any CH3 in here. There's another table. There is another table as well for the energy strains, and I would include those values as well. If let's see, gosh, okay, so it's not found in here. Yeah, it's not found in here. So I think it's 0.9. So what I have here, these are the energy values that I have for this structure. So what I have for this structure is, gosh, two CH3s in there. And remember, what is gosh? Gosh is whenever your groups are 60 degrees away from each other. So if you have two big groups that are 60 degrees away from each other, so here you do have two gosh interactions, a gosh between those two CH3s and a gosh between the CH3 and the other CH3 in there. So if I ask you, it's actually CH2, CH3. So if I ask you, go ahead and calculate the energy for this structure, you look at the table, I would give you those values over there. So you look at those values and you add them up, and you would get the energy for the structure. You don't have any other interaction other than Gauss. Normally, staggered only has Gauss interactions where the groups are 60 degrees away from each other. Let's have another example here. And you will see something like this in your exam, and there is something like this in the practice as well. So something like this where I ask you go ahead and change this into a Newman projection. So the way that I'm saying it, guys, this is an eclipse. It is not a staggered. See the difference between this and that. So what I'm seeing over here, if I look at the carbon number 2 from this angle, what I'm seeing is the OH eclipsing with the CH3, with the chlorine, I mean. So there's a zero dihedral angle between the OH and the chlorine. There's a zero dihedral angle between the CH3 and the ethyl. And there's a zero dihedral angle between those two hydrogens in there. So if I want to go ahead and draw the Newman projection in here, okay, for this one, I'm seeing first carbon number 2. This is what I am seeing. Okay, so what I have here with carbon number 2 is an eclipse. This is what I have. And so for the eclipse, um, carbon number 2 is connected to um, the OH. Or okay, so you do have the option because there's a rotation in there. So you do have the option to start with any one of those. But so you do have your OH in there. It is in plane versus the CH3 versus the hydrogen. Remember that anything which is on the side, this makes it a little bit easier. Anything which is on this side is in front, and anything which is on this other side is behind. Yeah, that will make it a little bit easier whenever you want to change this. If you are seeing the stereochemistry of this chiral center, then you know that this CH3 over here is going to be, here you go. So this CH3, since it is in front, is going to be in front. And this hydrogen there is behind, so it's going to be on the side over here. And this is going to be your OH. So that's going to be carbon number 2. Carbon number 3 is at the back. And I want it to be eclipse, because this is the structure of the eclipse in there. So see, the OH and the chlorine, both, they are zero dihedral angle. So definitely the chlorine is going to be here. It's a zero dihedral angle. And then these two hydrogens are on the same, they are basically a zero dihedral angle because they are both behind. So this is a hydrogen here. And then you do have your ethyl group, which is basically bisecting, or it is on the CH3. It's laying on the CH3 there, so it's going to be a CH2 CH3. So here you do have the energy strain for this one is really high because it is eclipse in there. So what are the energy values for this one? Actually, what you have is a hydrogen. Sorry, it's an OH Cl eclipse. This is what you have. It's an OHCl eclipse. I would give you the energy values for all of those. And then you would have the two hydrogen eclipse, so the HH eclipse. You can add those up. And then you do have the hydrogen CH2, CH3 eclipse. So basically you add all of these up and that will be the energy value for your structure in there. Okay. Yeah. So if I have now the Newman projection and I want to change that into a structure, so it says like draw the structure for this one. It's pretty much straightforward where you do look at the two carbons in there. So I'm just going to go ahead and look from here. I'm going to see this carbon and then I'm going to see the carbon at the back. So I'm going to see this carbon and then I'm going to see the carbon at the back. And for this carbon, what do I have? Just to draw it as you see it. It makes it really easier. And then you can change it into a skeletal form. So I have a CH2, CH2, and then a CH3. And then I have a chlorine versus a CH3 in there. And then this is the stagger. And then a carbon at the back has what? It does have CH2, CH3, and two hydrogens in there. So I'm just going to draw the hydrogen and then the other hydrogen and then the CH2 and then the CH3. So this is basically the structure. If they want it to be a skeletal structure, well, so if they want it to be a skeletal structure, then simply what you do is you highlight your longest carbon chain. This is going to be your longest carbon chain in there. Count it: 1, 2, 3, 4, 5, 6, and 7. So you do have 7 carbons in there. So we're going to draw our 7 carbons. 1, 2, 3, 4, 5, 6, and 7. I would go ahead and 1, 2, 3, 4. 1, 2, 3, and 4. So it really doesn't matter how you number in there. 1, 2, 3, and 4. Okay, so if I number from here 1, 2, 3, 4, that is 5. This is 6, and this is 7. On carbon number 4, so 1, 2, 3, 4, 5, 6, and 7. On carbon number 4, you do have a CH3. And on carbon number 4, you do have a chlorine in there. So this is it. So this is the structure for this one over here. Okay. Now, when they ask you what's the energy for this structure, again, since it's eclipse, since it's a staggered, it's not eclipse. The only energy that we care about is the gauche when the groups are 60 degrees away from each other. So this is gauche. This is gauche over here. Pretty much this is it. So you have to look at the table for a CH3, CH2, CH3 gauche interaction. And again, if you don't find it in the table, I'll give it to you in the given in the question. And then a Cl, CH2, CH3 gauche interaction. Add those up, and that will be the energy for your structure. For this one, you do have eclipse here. So these two need to be eclipse, these two eclipse, and these two eclipse there. So again, you find the energy for the eclipse for all of these, add them up, and that will be the energy for your structure. Okay, so this is one thing that I was asked about. Another thing that I was asked about is the chair conformation. Okay, so this is another thing that I was asked about, is to draw the chair conformation. Now, again, I'm going to refer to that table that I posted over here, and these are the diaxial interactions for all the groups in there. So these are all the diaxial interactions, and I would give you also the values in the given whenever I ask you about them. So in this kind of question, it's to draw the most stable chair conformation of the following. I'm going to read this note over here, that always the most stable chair conformation is whenever you have all your groups to be in the equatorial position, or you have the lowest energy chair conformation. So I would start by locating where are these groups. I can start numbering anywhere I want because I'm not numbering for the sake of naming. Okay, so I'm just going to go ahead and start having this to be carbon number 1, this to be carbon number 2, this is going to be 3, and this is going to be 4. You can number, as I said, anywhere you want. This is 5 and this is 6. And then carbon number 2 has the hydrogen, which is up. This group is up, and this group is up. It's very important to locate where these groups are. And then go ahead and draw your chair conformation. So we're going to draw both the chair conformers in there. So we're going to draw both of them. You're going to draw the chair, and you're going to draw its flip. And then we're going to determine where these groups are. And the chair conformation that has all its groups on the equatorial will be the most stable one. Or if it has the least energy, then it will be the most stable one. And this is why I'm giving you the energy over here, because sometimes it's so hard to determine if all the groups are not on the equatorial position. You have your okay, so we have here, I'm going to start with carbon number 1 being up there. I always like to start carbon 1 being here, carbon 2, carbon 3, carbon 4, and carbon 5, and carbon 6. When you flip, carbon 1 will be here. It's going to be 2, it's going to be 3, it's going to be 4, it's going to be 5, it's going to be 6. You can go by 1, 2 like this, or 1, 2 like that. It really doesn't matter. But normally we flip carbon 1, we flip carbon number 4. So these are the ones that normally we flip in there. Okay. Now when you flip, the axial turns into equatorial, but up stays up and down stays down. This is why I did put those as up and going down because you want to make sure to keep the same orientation. So on carbon number 1, you do have the CH double bond CH2 to be up, and up means axial in this type of carbon, carbon number 1. So this is the CH double bond and the CH2 there. Carbon number 2 up is equatorial. This is the hydrogen. And carbon number 4 up is equatorial, and this is the hydrogen. This is the bromine, I'm sorry. It is the bromine in there. Let's do the flip. Equatorial, axial becomes equatorial. Equatorial becomes axial, but up stays up, down stays down. Okay, so this one is axial. It becomes equatorial. But see, it's still up. It's still up. Okay. For carbon number 2, it is up. It's equatorial. It becomes axial. It's still up. And for carbon number 4, it is equatorial. It became axial, and it's still up as well. Good. Again, if all the groups are equatorial, then this is the most stable one. But if you have some axial, some equatorial, then in this case, and the groups are different, then in this case you would need the energy to determine which one is the most stable. The one which is the most stable is the one which is the lowest in energy. And the energy is determined by the diaxial interactions. So if your groups are on the equatorial, they will not do any energy interaction. So only the one that is on the axial is the one that's going to do interaction with the axial groups. So this one is up, right? It's on the axial. So it's going to do interaction with all the axial groups that are up. So on 5, I do have a hydrogen that is axial, and on 3, I have a hydrogen that is axial. So this is the 1,3 diaxial interaction in there. So I do have 2 hydrogen CH double bond CH2 interactions there. These are the diaxial interactions, so it's going to be 6.2 times 2. So this is the energy for this structure. Versus over here, what do I have? Again, the groups that are on the equatorial position will not do any energy interactions. The one on the axial will do energy interactions with the other groups that are on the axial position. So for the bromine over here, so the bromine is axial, so it's going to do an interaction with those 2 hydrogens in there. So here you go. So you're going to have a hydrogen, bromine, 2 hydrogen and bromine diaxial interaction, so it's going to be 2 times 2.5. Okay. You also have hydrogen. Okay. So you also have, let's say, you also have a hydrogen diaxial interaction, but it's only one because the second one is not there. So you also have a hydrogen diaxial interaction. Let me go to the table in there since I didn't list it. Okay. Is it there? Hydrogen, probably, maybe it is the value that I'm listing here is in kilojoules. I believe it's 0.9 or something. So this one is still going to be more energy. Okay, so this one's still going to be more energy in there. I believe this one is 0.9. So add those up in there. This one is going to be more energy. It's going to be less stable. Guys, if it is less stable, and this is one is going to be the more or the most stable because its energy is lower, then definitely this chair conformation exists as a higher percentage. So if I'm drawing the equilibrium is going to be like that, being this one to be as a higher percentage, and this one's going to be at a lower percentage. So once you want to go ahead and figure out where the groups are going to be, this group needs to be on the equatorial position, this one on the axial, and this one on the axial for it to be in the most stable conformation. So this is how you determine the stability. Okay, hope this helps. If you have any additional questions, please let me know.